So this was the task list that the kids from Friday's class worked with. So our homework from last class was the puzzles. If you need a copy, I have a few left, but not enough for everybody who just doesn't want to look in their backpack or binder for it. There's a difference. Some kids want a copy because I wasn't here, and some kids want a copy because I'm too lazy to look for it. Do you ever have that where you go back in your backpack and you find double copies of everything that you took an extra, right? Not doing. All right, so there was a quadratic and a ratios review. The quadratic is really a pretty cool thing, and Carl and I were talking about it this morning because it's talking about the relationship between FOILing and factoring, and I think that that's kind of cool. So I'm going to ask Molly, can you read me the problem number 1 that has the two binomial expressions? It's what? X
plus 5, and then x plus 2.
X plus 2. Okay, we're going to stop there. So when you have that expression, let me throw some vocabulary at you. Are you ready? Those are binomial expressions. Binomial, like a bicycle, has 2. So 2 expressions. It has a variable and it has a constant. That's a binomial expression. 2 expressions, 2 terms, 2 things being added to each other. And I'm multiplying 2 binomials together. We end up having to do the double distributive property, and the shortcut or the mnemonic that we use to help you remember how to do that is called FOIL. And the FOIL stands for first, outer, inner, last. And what you end up doing is multiplying your first terms, x times x is x squared. You go ahead and you multiply your outside terms, which is going to be 2 times x is 2x. You multiply your inside terms, and then you multiply your last terms. And in most of our binomial situations, when we are multiplying them, if it's the same variable to the same power, your middle terms will be able to be combined. So you have a little bit of work to do. X squared plus 7x plus 10. So what the worksheet wanted you to do, oops, that's not what I wanted. Hold on, wrong thing. Let me click on this instead. What the worksheet wanted you to do was take a look at what they have written down as the simplified version of that multiplication. Everybody pay attention to this. What's on the left is not simplified. What's on the right is simplified. So they wanted you to look at what's on the right and see if it matches. And if it is true, you circle it. And if it's not true, then you don't circle it and you don't add it to the puzzle below. You okay with that? So maybe you want to do this backwards. Maybe you want to work from right to left. So instead of doing all this first, outer, inner, last multiplication, maybe what you want to do is instead look over here and say, I wonder how I break this down into the 2 things that are multiplied to get it. This is what we call a quadratic expression. It's quadratic because the power on x is 2. Yeah, and it's simplified. I've put all of my things together, so there's no way for me to look at this. And if I asked you to break this down into its factors, you're like, no can do. I can't take anything out of it. I can't, like, nothing's working. So our technique of factoring, this is where we talk about what it means to factor, our technique of factoring, and this is where I told you the joke about the kid that said, oh, draw the butt cheeks. Remember I told you that? He didn't know where to start, and I said, oh, draw your parentheses, and I was doing this with my hands to show him that template, and he goes, oh, the butt cheeks. So now, and that was like 15 years ago, and I'm still telling the story, because once you see it, you can't unsee it. You're welcome. So your first step is always going to be to split your x's. because x times x is x squared. So what you're doing is you're working backwards. Your first terms, first, outer, inner, last, your first two terms were multiplied together to give you x squared. The only way to get x squared is x times x. Thumbs up if that makes sense to you. All right. Your last terms are going to give you this number 10. If you want to sit and look at all the different possibilities of how to get 10, there you go. These factor charts that I like to draw, I go ahead through it in a very systematic. Does 1 go in? Does 2 go in? Does 3 go in? Does 4 go in? Does 5 go in? And I keep going until I get my repeat factor. This is my swing around. My commutative property says it doesn't matter what order you multiply together. So 2 times 5 is the same as 5 times 2. I don't have to write it twice. So I'm going to go through and divide 1 in, divide 2 in, divide 3 in, divide 4 in, divide 5 in, up, repeat. Now I know I'm done. Does my factor table make sense to you? So I know that these numbers here are going to come from this chart here. So now I go ahead and I look at my signs. If my product is positive, my middle term is going to be a sum. If my product is negative, my middle term is a difference. So because my product is positive, I know these two signs match. And then I'm looking for two numbers that add up to my middle term. So I know that one of these is a 2 and one of these is a 5. Nobody cares which one, because again, that commutative property. You okay with that? Now when I try to look at that sign, it's going to be the sign of this middle term that determines what my signs are. I know they match, and I know they're both positive because 5x's plus 2x's is positive 7x's. If that sign was a subtraction sign, it would have been x minus 2 and x minus 5. Are you with me on that? So what's cool about this worksheet is I don't care if you FOIL to check or if you factor to check. You can work from left to right, right to left to check each of these things to see if they work out. Your job is to see if they work out. So what I want from you, if you didn't get a chance to finish the homework, if you didn't have the time, if you weren't here and you didn't get a piece of paper, then that's something that you can work on, because I'm going to want this sheet turned in at some point that you finish all this work. Make sense? Okay. So I'm asking you to do a quadratic review, give me the puzzle answer, and I want you to tell me the difference between foiling and factoring and using one of the worksheets as your answer. I'm watching Paige and Molly, they're both taking notes with me today. They already have their one example, but then I want them to write it out. What is the difference? And explain it to me. Make sense? This next problem talks about on the back of the worksheet your review on ratios. Some of these problems were tricky. And it was interesting to see that some of them are talking about ratio problems. And some of them talk about what we call inverse variation. And I think the one with the chemistry, you only have so much material, so how am I going to divide differently to be able to accommodate those new students that join the class? So what I want is for you to talk about which was the hardest problem for you to solve in your puzzle answer. So I want that turned in to me. Ideally, we'll have some work time today. And during that work time, you can work on this, you can work on your Delta Math that was from this assignment, or you can work on today's Delta Math. This piece of paper is going to be due at the end of our unit. So I'm going to give you a lot of time to work on it, but I want you to keep plugging away. The Delta Math has some unit skills review. The quadratic proportions is going to put you into two circumstances. Some of the quadratics that you are going to solve are going to have this middle term. Some of them are not, and I want you to pay attention to how you solve each of them. You have an exercise on simplifying radicals, and the biggest frustration about radicals is kids keep wanting a button. Like, you know how you have math frac enter, and you wanna be like, I wanna get it in and out of being a fraction by letting this calculator tell me how to do it, there is no button like that for radicals. But the calculator can help you. So that is the one where we go into my y is equal to button and I type in, for example, 36 divided by x. If I go to my table of values, that's going to give me all of my factors of 36. God bless you. So my conversation is how can that table help you simplify radicals? Go ahead.
So don't we have to do x squared for that trick, or do we just do x?
Just x.
Oh.
All right. So that's what I'm asking. How can this process help you? The rest of the problems in the Delta math are lots of Pythagoras conversations. We're going back and reviewing the Pythagorean theorem, looking at answers rounded, looking at answers with simplified radicals, looking at story problems, looking at the converse to prove what different kinds of angles and triangles that we're looking at. So that's what's on this paper that the red kids had on Friday. So you now have this paper, but we are not working on this. We're moving ahead, and I'm going to expect this piece of paper turned in by the end of the unit after you have finished all of that review work and had a chance to fill in. Everybody okay with that? Yeah? All right. So you can tuck that piece of paper away. Would you please do rock, paper, scissors with your partner and see who wants to go for a walk? And, all right, so take a look at your packet, please. Please make sure that your name and period is on it so that if something were to happen, I can get it back to you. Hey, we are perfectly timed for our 5 weeks of consistency with school. We told you this last week. I'm so excited for these next 5 weeks. 1 down, 4 to go. Because the amount of focused energy and conversation that we have matters. So we're going to start off today talking about similarity in right triangles. And next class we're going to talk about some special right triangles. Again, not a lot of creativity in naming things in mathematics. We call them 30, 60, 90 triangles. Guess what that means?
30, 60, 90.
Their angles are 30, 60, 90. Hey, what do you think about the 45, 45, 90 triangle? Yeah, those are their names. Not a lot of creativity. That's like if, Bridger was named Baby Boy Poultry. Like, not a lot of creativity, right? So we have 30, 60, 90, 45, 45, 90. We're going to have a quick homework quiz. In this unit is a bunch of new stuff and things that you need to memorize, things you need to do, things you need to have at the front of your brain. So we're giving you some little homework quizzes that are going to add up to one bigger formative grade. And that homework quiz is going to make sure that everyone's staying honest and doing the work that we need them doing, asking the questions that they need to ask. What happens on Friday is my favorite lesson, introducing you to these new trigonometric ratios. And some of you had asked me on the math testing, what's sin, cos, and tan? Those are sine, cosine, and tangent. Those are names that they've given to trigonometric ratios. Completely unlike everything in mathematics, these were creatively named. So sometimes kids have a hard time remembering them. It's sine, not sin. It's cosine, not cos, and tangent. We're going to talk about those special ratios. Then we're going to talk about some angles of elevation and depression, have another quick quiz that adds to your formative grade, some review and practice. So the test is super quick. You're already looking at a test in 2 weeks from today. So it's a quick unit, but it's exciting for me. It's what I like to teach because you've never seen some of it before. So from having the map testing and having those questions, you're curious. So I can't wait to tell you what it's all about. The first thing that we're going to talk about is this similarity in right triangles. So I've given you all a rectangle. You're welcome. You have picked up a pair of scissors. Bravo. And what I want you to do is I want you to cut along the solid lines, and you're going to create 3 triangles. And I tried to mix up the colors of everyone around you. So after you do a really good job cutting with nice straight lines and even scissor marks, your kindergartner teacher would be so proud of you. What I want you to do is kind of do a swap and trade triangles with the people around you so that you have 3 different colors. You're going to have a small, and a medium, and a large triangle. I want you to arrange and label the short leg, long leg, and hypotenuse on both sides of each right triangle as follows. I'll give you a couple minutes to get that done in your mark and set code. Once that diagonal divided your rectangle into 2 congruent right triangles, this line segment here is the altitude to the hypotenuse of one of the triangles. So that segment that you cut on created a medium and a small triangle. So if you look at each of these triangles like this, you can prove that they have angle-angle similarity. Now the right angle isn't a shock to you, but you had a question on your review where it said, are all right triangles, all right scaling triangles similar? And you're like, no, not always, not given, right? But check it out. These ones are, because these have angle-angle similarity. So that's kind of crazy. Are you kidding me that this angle that I cut in different locations matches up and is the same? And you can go ahead and collect all your angles down here on your smallest angle opposite the shortest side, and you can say, holy cow, check it out, they're all the same angle. So you do have angle-angle similarity. And when you look at something like this, is your mind going side splitter theorem? Is your mind thinking those lines are parallel? Is your mind thinking all these angles that are the same in those pieces? We're going to be talking about some of that and adding that to what we're doing today. But this is a holy cow wow moment for mathematicians. Let's review what we did. We drew a diagonal and a rectangle and gave us 2 congruent triangles. No big deal with that. But then I drew an altitude to the hypotenuse of one of my big triangles, and it gave me 3 similar triangles. And in this lesson especially, Carl, heads up, in this lesson especially, the more fluent you get in smallest angle opposite smallest side, largest angle opposite largest side, medium angle opposite medium side, that's going to help you keep track of these triangles. So if you set them up in this orientation and labeled everything A, B, C, Y, H, A, and H, X, B, you're like, these are really weird letters, and I wanted you to label them on both sides. Everybody okay with that? It is a trick to be able to put the triangles back into the correct orientation. And it's funny watching kids flip it around to make sure that you can put the small and the medium together like this, and then put that together like this with our big. And it does have some flipping around. Go ahead and put them back. Tell me what you notice with your letterings. When you put your triangles back together again, do you notice that the H's match up? Do you notice some of my sides, my repeat sides, match up? So your repeat sides, you should be able to make that rectangular shape again. And if you're sitting there, check in with your partner. If you're sitting there without that rectangle, something needs to be flipped or turned or twisted to get yourself back to that orientation. Your next conversations with your partners are like this. I would like you to complete these ratios. It might be easiest to return your triangles to this orientation so that you are comparing corresponding sides of similar triangles. Make sense? Alright, turn to your partner and say, let's go. When we're doing similar ratios, it's interesting when we match this up. If I'm talking about comparing B to A, it's not sure if I'm talking about this B or that B. If you put your triangles together, those two B's are the same. So if I talk about B to A, that is the same as X is to H. Thumbs up if you and your partner got that. All right, when I talk about Y to H, that's going to be the same as H to X. Thumbs up if you got, go ahead. What's not?
So the first question, couldn't it also be Y to H? Because if you're looking at the second triangle, B to A in the second one, and then Y to H in the, or B to A in the first triangle and Y to H in the second one.
I wouldn't do that because B to A, I'm dealing with short side and hypotenuse here.
Oh, you did those.
So if I did, oh, are you talking about B to this A?
Yeah.
So B to this A is going to give me
No.
H to Y.
Yeah.
See how it's reversed? It's not corresponding. Alright. Let's talk about 3. X is to B. X is to B as B is to C. How'd you do with that one? Alright. If I talk about B is to C as what is to H?
Yeah.
B is to C as A is to H, right? Or H is to A? Do you buy that?
Yeah.
And then Y is to A as, did you get H is to B?
Yeah.
You make that a little bigger. And then when we talk about A, if I'm comparing A to C at the same time as I'm comparing what to A?
Y.
Very good. Y is to A. Now what I want you to do is put your triangles back into their orientation where you have these two triangles next to each other like this. We're not going to worry about the big triangle for right now. I want you to match up your H's with your triangle because what you've just figured out is a bunch of relationships that exist in right triangles. So if you look at your triangles and you're just matching up this conversation with this triangle here, do you agree that this is your H? Yeah? That's the height of that triangle. What you just proved is that height is the geometric mean between the two sides, X and Y. So if I look at this measure here, it says X, and this Y here. Do you see how that H is the geometric mean? That's our first theorem we're learning today, is that the altitude to the hypotenuse of a right triangle is the geometric mean between the two pieces that it creates. It divides that hypotenuse into two pieces, X and Y. And that height is that geometric mean. Now we've got two other conversations where we can see some geometric means happening. So I see a geometric mean story here where A and B are both in those geometric means. Both of them, A and B, if I look at where they are on the triangles, they are the hypotenuse of the small and medium triangle and the legs of the large triangle. Make sure you can see this. Look at your triangles and make sure you understand what I'm talking about. Carl, put your head up. That A and that B are serving double duty. Do you see how in one reference they're the hypotenuse? Do you see how in another story they are the legs of the big original triangle? That's kind of cool, isn't it? So those legs of the large triangle are the geometric means between these values, x and y, and the hypotenuse. So we're going to learn that that relationship exists too. So when we look at our notes and we talk about what special patterns or relationships do we notice, the conversation is about H doing double duty and about A and B doing double duty. So this H, this side H is listed twice. This altitude to the hypotenuse of a right triangle is both the long leg of the small triangle and the short leg of the medium triangle. These A and B sides, B is the hypotenuse of the little triangle and the short leg of the big triangle. And this side A is the long leg of the big triangle and the hypotenuse of the medium triangle. Each of these sides does double duty. And the interesting thing is, I talked about things matching up, and Molly said my C doesn't match up. When I look at putting my pieces together, my H's matched up, but my C didn't. And the interesting thing is, I know that X plus Y is going to be equal to C because that altitude divides that hypotenuse into two pieces, X and Y. So looking at these pieces and understanding, putting them in the orientation where I can match up corresponding sides of similar triangles, takes a little bit of time and it can be confusing. So what Euclid did was once he discovered these relationships, he's like, you know what, we're gonna make some rules. And every single one of these problems can be solved without the rules if you wanna take the time to change these triangles into this orientation so you can see corresponding sides. But you agree that that can be confusing with the flipping around and the spinning and the rotating to make them match up. So here's the rules. The right triangle similarity theorem is something that we used, that we've already proven using a physical proof. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles' forms are similar to the right triangle and each other. Here's our altitude to the hypotenuse. So make sure you understand what this word is. Altitude is drawn to the hypotenuse of a right triangle. Then I can have these three similar triangles. You have a physical proof of this. We went ahead and did a physical proof of this theorem. So we all agree that it matches because we had angle similarity, no problem. Feel good about that? All right, on to the next part. Now we have some geometric mean theorems, and we have some corollaries that go like this. In a right triangle, the altitude from the right angle to the hypotenuse is going to divide the hypotenuse into two segments, x and y. The length of the altitude is the geometric mean of the lengths of the two segments. So this is what we're talking about here, the altitude from the right angle. So here's our right angle, 90 degrees. And what's important to think about is our original triangle is this original right triangle. Now you're used to seeing right triangles always sitting up. So it's different for us to see this triangle kind of laying down. But what we care the most about is this altitude to the hypotenuse of a right triangle. The altitude from the right angle to the hypotenuse divides the hypotenuse into two segments, x and y. This hypotenuse is going to be the geometric mean between x and y. When we learn how to set up these ratios, sometimes you'll hear me refer to this one as the loop-de-loop. So x is to h as h is to y. So that's a relationship that you proved on the front page. X and y are the two pieces of the hypotenuse. H is their geometric mean. Multiply them together, take the square root. Our second corollary deals with the other legs that do double duty. You know you have this B and this A that do double duty, and they are both the geometric mean between this piece that it's touching and this whole side. So B is going to be the geometric mean between X and C. And it has to do with those ratios that you set up on the front already. Because that B is doing double duty. It's both a hypotenuse and a short leg. So it's a geometric mean between the other hypotenuse and the other short leg. Corresponding sides of similar right triangles. When we talk about A is going to be the same thing. This A is the geometric mean between this piece that it's touching and this whole length of C. So this one triangle shows us the two legs of my original triangle, the big triangle, are the geometric mean between the corresponding side of either the small and the medium and the hypotenuse. Some kids like to do a loop-de-loop conversation with this one. Some kids find it too forced. This one everybody sees and knows. Some kids like to talk about this conversation where I can go from B to the one it's touching and the whole. And then the reverse of that is going to be if you talk about A to the one that it's touching and the whole. If you don't like those loop-de-loops, don't muddy up your drawing, but they seem to help some kids who need a visual. All right, let's practice these. What they're going to give us is a bunch of problems that look like this. Now, if you want to take the time to redraw all three triangles and label them in matching orientations so that you can see corresponding sides, that will work. You can do that. But you're going to be exhausted because you're going to spend 3 times longer doing your homework than the kids that take the time to memorize. So what we're going to do is just get in the habit of writing some proportions. Do you see this loop-the-loop?
Yeah.
That means that X is going to be the geometric mean between the lengths of those two sides. That's a proportion you know how to solve. You're already on to the next problem while someone else is sketching similar triangles in the same orientation. X is both the short leg of the medium triangle and the long leg of the small triangle. That's why he's in that proportion twice, and he ends up being the geometric mean. X squared is equal to 32. X is going to be equal to 4 roots of 2 when I simplify that radical. Start paying attention to the radicals that you're simplifying, because you should be able to see that 32 is 16 times 2. 16, I can take the square root of that, and that's 4 roots of 2. You're going to be seeing the same numbers over and over and over again. Start paying attention. So it's like knowing what channel to get to your favorite show. You can do it automatically eventually. Let's talk about y. Y is going to be the geometric mean between the piece that is touching and the whole. So when I set up my proportion, y is the geometric mean between this small leg and this hypotenuse.
So it says 6.
Uh-huh. It doesn't say 6. What's the whole? Yeah. So that's going to be, and make sure if you need to tell yourself that that's the sum of those two pieces, make sure you have that down. Y is the geometric mean between the piece that it's touching. And you can take the time to go ahead and say, oh, here's a short leg, and I'm comparing it to short leg. Y is also the hypotenuse, and here's my hypotenuse. So you can match up those corresponding sides of similar triangles, easy peasy. So when I go to finish solving this one, I know that y squared is equal to 16, so y is equal to 4. No need to simplify my radicals there. It is time for you to make sure that you have your perfect squares memorized. It is time for you to make sure that you are thinking about and paying attention to the numbers that you use over and over again, because the quicker that you commit this to memory, force yourself, push yourself, pay attention, think about it. Oh, hello 16, I see you. These numbers need to be your best friends. You need to look for them in every single problem. Do you see factors of 4, 9, 16, 25, 36, 49, 64, 81, 100? Having those numbers in the front of your brain will make this whole unit significantly easier for you. All right, let's look at these practice problems. What I would like for you to do with your partner, don't solve, just write the proportions. So you and your partner think about right now, if you're writing a proportion, you want to say this is equal to that. This is equal to that. This is equal to that. Some of them have solving for x and y, so this one's going to need two proportions. We're at the point now where solving a proportion is not our problem. We did that last unit. Writing the proportions is what we want to get right. And a lot of you are lazy with your proportions. You neglect to put the equal sign. And if you forget that equal sign, that's not a proportion. You've just written down some chicken scratch. So turn to your partner and talk about these proportions. And you mark and say, go. So it's so important that you get this right. And if you sat there and you drew all your ratios and you copied my work and you didn't put your brain into doing it, you're missing out on my favorite comment I just heard. And I'm going to remember it and talk about it in every single class. Like, I was so confused, but I'm loving it. Like, what a great statement. I was so confused, but I'm loving it. Like, how fun is it to watch your brain figure out something new? Like, what a great task that is. Okay, this is a puzzle, and I'm totally going to get it. If you look at this, let's just look at this first shape here. X is the geometric mean between the piece that it's touching, if you want to do your loop-de-loop, the piece that is touching and the whole. Now you can already know, Jasmine's like, wait a minute, she already tried to correct me on the one that we did earlier, and now she knows I got to add them together. I got to remember to do that. So that mistake that she made is going to lead her to not making that mistake anymore. So if you did not do this work with your partner and you waited for me to fill in the answers, you're now in the position of you didn't get to mess up. You didn't get to know, is that a mistake that you're going to make? Oh, gosh, I gotta remember to add them together. Because Jasmine's now smarter for it. And until you make yourself vulnerable and do the math, you might not know what you need to get better at. Take a look at Y. I can see that this here is two things. It's the long leg of the big triangle and the hypotenuse of the medium triangle. That Y is going to be the geometric mean between the piece that it's touching and the whole.
Do we have to write down the Y one too?
Yes. Anytime we ask you to solve for the variable, you want you to write a ratio. And how crazy is it that with that one sketch, I can have two variables and have two different problems from one question.
Why do you have the exponent of y on the x?
I don't, that just happens to be where the picture is.
Oh, okay. I was so confused. for a
Yeah,
second. I was
no,
like,
that's just, if I scooch this over, that's just where the
Okay.
variable is on the picture. Go ahead.
I'm a little bit confused on what you mean by the piece that it's touching.
So this altitude to the hypotenuse is going to divide this hypotenuse, that's a tongue twister. The altitude to the hypotenuse divides the hypotenuse into two pieces, 2 and 6. X is going to be the geometric mean between the piece that it's touching.
So like kind of pretend that that second triangle isn't there.
Right.
Okay.
So think about this, Jasmine. This X is going to be the geometric mean between the piece that it's touching and the hole. It's touching the 6, the hole is 8.
Okay.
Y is going to be the geometric mean. That's the one that's inside, and that's our easy loop-to-loop between the two pieces.
Does it matter if you put the 6 on the top?
No, because those are extremes that can be exchanged. So Molly's like, I put my 6 here and my 2 here, is that okay? Yes. Because these extremes can be exchanged. Think about your cross products, they're both going to be the same. Now this is a trick question. Because where X is not one of my 3 double duties. 10 is a double duty. This side of the triangle is the long leg of the little triangle and the short leg of the medium triangle. And these two sides of the triangle are my legs and my hypotenuse. 10, or where X is, he's not anything. So we need to recognize here that it's 10 that's doing the double duty. And if I want to solve for X, he is not in the geometric mean. And this is one of the most missed questions of the test. When we ask you to say 10 is the geometric mean between 4 and what number? That's what we had you writing. So all the geometric mean questions we've already had you been doing is setting you up for this conversation. So 10 is our geometric mean, not X in this one. Got it? All right, revisit your next row with your partner and commit yourself to saying, did we get them right? Double check them. Turn and talk about it. Go. All right, so check your work carefully with mine. And if you are an auditory learner, if you're somebody who needs to hear either a song or a jingle or a pattern, or if you've ever had that scary experience of hearing your teacher's voice inside your head, you're doing your homework, you're like, I can hear her in my head. What we want to do is make sure you understand why is the geometric mean, Molly, take this out of your ear. Why is the geometric mean between these two pieces? Here's your loop-de-loop. X is the geometric mean between the piece that is touching and the hole. Check out this problem. We've got all 3 variables to solve. Z is the geometric mean between those two pieces. There's our loop-to-loop. Y is the geometric mean between the piece that is touching and the hole. X is the geometric mean between the piece that is touching and the hole. Now this one's interesting. I'm going to need some information to solve for X, because when I look at this, 8 is the geometric mean between, or Y is the geometric mean between X and 8. And I know that Z is the geometric mean between the piece that's touching X and X plus 8. So in order for me to solve these, I need to focus on how the heck am I going to solve for X? And that's going to come from this conversation here. 12 is the geometric mean between the piece that is touching and the hole. So 12 is the geometric mean between the piece that it's touching And when I go to solve for x, that has to be that whole. I can't solve for z and y until I solve for x. And I'm telling you something, we're gonna mix this up all the time. So you have to be a thinker when you look at each of these problems. I heard a crazy video the other day, and it was a women's basketball coach, a women's college basketball coach, and she compared how kids learn, how her players learn. And she's a basketball coach, but she used a baseball analogy, so stick with me on this. She said the team is doing batting practice, and the coach puts each player in and gives them 30 fastballs. At the start, the player can't hit the fastballs, but at the end of 30 fastballs, he's hitting. Nice job. Next day, 30 knuckleballs. Can't hit them. By the end of the 30, no problem. Next day, curveballs. Can't hit them at the beginning, can't hit them by the end of those 30 balls. So we think, oh, that's good, because he's learned through that thing. That team is not going to do well because those batters have not been trained to think. You're better off, that's called block learning. You're better off in a position where you get some curve, some knuckle, some fast, and you have to make a decision. What you're looking at here is you making a decision. What you're looking at here is you're looking at each of these triangles and asking yourself, what am I looking at? And the baseball player who's dealt or is pitched to with an inconsistent, unpredictable pitch is learning more than just how to hit a fastball, knuckleball, curveball. That baseball player is learning to think and react and look for cues and make a decision about what's coming. That player does better in a game. Because very rarely in a baseball game does the pitcher say, I'm doing a fastball, are you ready? Does that happen? So we need to put ourselves in the position of where we're looking at each thing and being like, okay, I'm a thinker. Is that the altitude to the hypotenuse? Is that a loop-to-loop? Is that a leg of the original triangle? Is my variable in a position where it's not a part of a geometric mean? And that's what happens here. Being a thinker about what kind of problems you're looking at makes the biggest difference. All right, we have 18 minutes left. And what I would like you to do, your homework is going to be these 2 pages here where we're talking about solving for x. I don't want you starting here because you could do the whole assignment wrong and not know it. Where can you go to get feedback? There you go. Now, when you go on to Delta Math, you're going to see the homework that the Reds did. Skip that, and I would rather you doing this right triangle similarity assignment first. It estimates it'll take you about 15 minutes, so there's a very good chance that some of you finish it before you walk out the door. The small, medium, large triangles are for you to use to help you as you're learning this. Got it? Yeah. All right, take your computers out, make good use of your time.
What did you say about this one?